All right, so let's recall our case with 5 apples taken from a large population. Let's pretend that population average is known and population standard deviation is known. In this case, it's 9.4 and sigma will be 0.25. Yeah? Remember, this is how we compute z-scores. We take every value, subtract average, and divide to standard deviation. And that's exactly how to compute z-score for this value, right? So you can see it's 0.8. So it means that it's 0.8 standard deviations larger than the average. If you square it, we will get 0.64. Then we can compute it also for the second value. You can see it's symmetrically smaller than the average, so therefore the z-score is the same by absolute value but different by sign. And then we continue until we calculate z-scores and squared z-scores for all values. Now we can compute chi-square by taking a sum of all these values. So we got chi-square 13.6. Okay. Degrees of freedom is 5 because in this case we didn't use any statistics based on our sample. We computed all these z-scores based on the population parameters which we knew a priori. So therefore we didn't change the number of independent values, right? If you make a chi-square distribution for degrees of freedom equal to 5, you will find out that for 95% of the cases, this value should be between, this one is missing, so here you have 0.83, it's just a little bit hidden. So you can see that in 95% of the cases, this value should be between 0.83 and 12.83. However, in our case, it's beyond that. Well, that's also possible, right? So we had a probability of 5% to have it here. Now, let me show you how to do it if you don't know the population parameters. Let's say that we don't know the population mean, but still know the population sigma. In this case, we can replace population mean by computing sample mean, 9.5. And let's do all the computations again. So in this case, we compute z-score based on the sample mean instead of population mean. This one is 0.4, so this is 0.16. You can see how big the difference is, right? And so on and so forth. Then we compute chi-square by taking a sum of these values, right? And then you can see the chi-square, it looks like a little bit less extreme, right? So comparing to this one. However, the number of degrees of freedom in this case will be 4, not 5. Why? Because we don't have 5 independent z-scores anymore. Because now we have a link that makes one z-score depends on the other ones. So now we have 4 degrees of freedom, like we discussed also in block number 1 when I show you how to compute variance, right? So in this case, we need to make a distribution for 4 degrees of freedom, and then you can see that it also looks a little bit extreme in this case, right? Like we had it also before. Okay. Now let me show you how to use this knowledge to compute actually confidence interval for the variance. So far, I think it doesn't look very clear. Let me simplify task and use 3 values in my sample, just to make calculations easier. So if I want to compute z-score based on the sample average, then I need to do it like this, right? And then if I want to compute chi-square values based on the z-score, I can do it like this. So you can see the chi-square, it's a sum of squared z-scores. I have 3 values, so I have 3 z-scores. So this is a squared z-score for the first value. You can see it's x1 minus m divided to sigma, and then I square it, right? But I can replace it, just square the numerator, right? And the denominator, it will be the same. So this is it. So this is a squared z-score for the second value. And this is, I should have 3 here. This is a squared z-score for the third value, right? So this is a chi-squared value for my sample. Now you can see that we have sigma squared here, sigma squared here, sigma squared here. So we have the same denominator. It means that we can just combine this together and use it like this. So x3 here, okay? Now, this is our chi-squared. But look at this part. Does it resemble you something? Let me remind you one of the first lectures when we computed variance, right? So this is how we computed variance. And look at this one. So you have this part here as well. So what you have here, it's just a variance times n minus 1, right? So this is the formula for the variance, how to compute variance. And now if you look at this one, at this part, you can see it's exactly this one. Yeah. And if you multiply both sides to n minus 1, for example, we have n minus 1 here, n minus 1 here. So this will cancel out. So we will have exactly this part is equal to the variance of your sample times n minus 1. Let's replace this sum with this n minus 1 times s squared. So now we have a sample variance, and now we have the population variance, and we have a random score, right, which follows theoretical distribution. So chi-square distribution links the variance of your sample and the variance of your population, similarly like normal distribution links average of your sample and average of your population, right? So variance of your sample of size n divided to the variance of population multiplied by degrees of freedom follows chi-square distribution. So it means that you can do absolutely the same things like you did for average, in this case, for example, computing the confidence intervals. I can rewrite it like this. So the variance of your sample, it depends on the variance of your population divided to n minus 1 and random number. So remember, this is fixed, but this is the randomness. So this makes your variance of your sample randomness. So every time you take a new sample, the variance of your sample will be a random number because you have this randomness effect here. Okay. So now we have sample statistic, population parameter, and then we have chi-square score, which is described by theoretical distribution, and then we have degrees of freedom. And now look, this is what we learned for the average, right? It's the same. Sample statistic, population parameter, a score which follows theoretical distribution, and some additional, so in this case it's n and standard deviation, right? So you can see that like t distribution makes a link between m and mu via the distribution, the chi-square distribution makes a link between variance of your sample s squared and variance of population sigma squared via distribution, right? So you can see a very clear similarity here. Now let's use it to compute the confidence interval. First of all, we do the same things. We computed some statistics, average, standard deviation, variance. So we have variance, we have standard deviation, we have average. Actually, we don't need average. You can see we don't have average here. But now what we can do, we can compute the chi-squared values, the theoretical chi-squared values for left and right boundary, right? So for the left boundary, if we have 0.95% here, so here we have 0.025. And this is how to compute the chi-square value for the left boundary. It's this one. Now we compute the chi-squared value for the right boundary. So here, this one. So now it's 0.95 plus 0.025, it's 0.975. 4 degrees of freedom, it's this one. And now we can use this knowledge to compute confidence interval, right? So we know that the variance of your population can be computed by taking variance of your sample, multiply to n minus 1, and then divide to this critical chi-square values that we just computed. So this is the computed critical chi-square values for left and right boundary. These are statistics that we need. Now let's do that. So the upper boundary can be computed by taking the variance of your sample, 0.2, times number of degrees of freedom, it's 4, and then divide to the smallest part, or the smallest chi-square, 0.48. So this is our estimate for the largest variance of population. Now we can do the same for the smallest variance of population. We take sample variance, multiply to degrees of freedom, and take this part. So this the largest chi-square value. So this is the smallest expected variance for the population. And since it's a variance, so now we have the confidence interval for the variance, we can compute also confidence interval for standard deviation, because we know that standard deviation is just square root of the variance. So we simply take a square root of this value, and that's the upper boundary for standard deviation. We take a square root of this value and get lower boundary for the standard deviation. So now we have 95% confidence interval for standard deviation of our population. So this is a variability of sugar content in different apples in the whole garden. We don't know exactly how big is it. In our sample, it was 0.45 grams per 100 gram of apple mass. But in the population, we can expect anything between 0.26 and 1.29. So this is our estimate how big the variation of sugar content from apple to apple in the whole population. So that's it. And then you can see the procedure is absolutely identical, right? So we need to know distribution that links population parameter and sample statistics. And then we use this distribution to compute possible values of population parameter by using the quantile function of the theoretical distribution. And then you will see this over and over and over again. Once you understand how it works, you will have no problem with the rest of the calculations in this course. Okay. There will be no dedicated lectures for exercises because we already did all the necessary exercises during the other videos. So this concludes the learning sequence about confidence intervals. And in the next learning sequence, we will continue talking about relationship between sample statistics and population parameters. And this time it will be hypothesis testing.